Hi everyone, welcome back. In this video, we'll create some ports for our device. The ports will be usable for simulations and for our circuit connections and also drawing large-scale circuit layouts. So to start off, what we'll do is we'll first go to the top and enable our trace template. We'll need it for this example. Underneath the parameters at the same indentation, we'll also add a new function called _default trace template. I believe this is needed for some default functions. We just won't go into too deep of details regarding this item. And then it'll return the PDK's SI wire waveguide template. And then now let's return back to the layout section. And in the layout section, at the same indentation of the functions, we'll create a new function called _generate ports. And you'll see that it has a input for a variable called ports. We'll return that at the very end. So return ports. And what this does is it's similar to the LMs list we mentioned earlier. It's just a list of ports that we're going to put into it. So next we can actually declare the ports objects. The first thing to do is we're going to assign trace template to our parameter value. We'll need this to make sure connections work automatically. Next, what we'll want to do is we'll create the actual port. So ports as the list will get appended by our object called i3 optical port. And this optical port object takes in a name, so we'll call it in1. It'll also take in a position, which will be an x and y coordinate position. So for now, we'll put it at 0, 0 at the beginning of our device. Next, it'll take in an angle. So we'll set this value to 180. And it's 180 because the convention is the angle with respect to the x-axis, and it's always facing outwards. So if we're in the input port, we want to face it towards the negative x direction, facing it outwards that way. So we can leave a little note here, angle with respect to the x-axis, always facing outwards from the port. And that's why it's 180. And then finally, for the final value to pass in is a trace template, and we'll set it to our default trace template. And then next, we'll have an output port as well. So we'll copy the same code, and we'll put it down here. We'll rename it as output1 or out1. And then this time, the position has to be at the very end of the device. Luckily for us, we already did that exercise last video. So it's self.period multiply self.period number, and that should put us right at the very end of the device. And we'll want the angle to be 0 because it wants to face towards the positive x direction. And with that, we can take a look at our work. This time, we'll re-enable visualizing in the Python editor. The reason is because ports don't get exported to the GDS, so it's only visually viewable in the Python window, or if we make another circuit design somewhere. And I think I have a misspelling. Yes, it's trace template, not trace templates. So I believe this is the issue right here, line 41. So we'll run it again. And we should see our device with ports labeled. So that looks good. Our input ports at the beginning, our output ports at the end. We can zoom in on it if we like. And everything looks like it's working properly. So with that, we can do some cleanup. So first thing I want to clean up is we had that SWG Boolean earlier, and that determines if we draw the center waveguide or not. So why don't we add that in and have it do something? So this is our center waveguide. I will leave a comment here. And then what we'll do is we'll add in that Boolean. So if SWG equal true, or we can just say if SWG, if it's not true, then we will draw the waveguide. Otherwise, if it's true, we won't draw. So now that Boolean is doing something. The next thing we want to do is, why don't we add a cladding to the whole geometry. So underneath the waveguide, we'll add a new section called cladding. And if you recall again, cladding has a Boolean property. If it's true, then we want to draw the cladding. So for here, we'll say if cladding. This means that if cladding is true, or sorry, if self.cladding, then we'll do something. So if it's true, then we will draw a rectangle. We can reuse the waveguide one just to save ourselves some time, because the position should be the same. We just need to increase the box size. So we don't have to increase the X span, but we do want to increase the Y span. So the Y span right now only goes to the waveguide. What we'll do is instead we'll have it be the waveguide. It'll include the corrugation width, so plus self.dw. We'll double it for either side of the corrugation width, and then we'll also add in 2 microns of spacing. So this should be a lot of distance for us, and it should properly cover the device. Also, we want to change the layer from device layer to cladding layer. And with that, we can check our work again. So we'll run it. And you'll see now we added a cladding layer to our device. We can zoom in on it. The pink parts are cladding layer. And then we can also view it in our layout editor. So here we see it added a cladding layer as well, and everything worked correctly. Ends at the correct place. There's sufficient distance from the waveguide. So everything looks good. One other trick I want to showcase here is at the very bottom, we can also view the cross-section of the device. So the cross-section function is also in device layout, and it's called cross-section. And then in it, we'll have to give it a few things. So first is the cross-section path. And this will be i3.shape. It's a square bracket, and then we give it 2 locations. So this location is where we want to slice the object to look at the cross-section. So just copy it over from my finished code. And then next is we want to tell it the process flow so it can draw the layers properly. So this is actually loaded from the PDK. And then finally, once we have that, we can call a .visualize function by itself. And we'll give it a run. So you should see the first window pop up, and then it'll write to a GDS, and then it'll show us our second window where the cross-section is. So our first window, and there's our second window. And this is a great way to view your devices if they're multi-layer and very complex. So you can see we have silicon for our main device here, and then silicon oxide for the cladding. So everything works well. I'm going to disable this for now, because aside from this demonstration, there isn't much functionality I want to showcase past this. And let's see if there's any further items to add. So I think what we can do is we'll also add in some more functionality in setup of the next video. So the first thing we want to add is a new section called simulation. And what this part will do is we'll add in a Boolean called simulation geometry. So when you do a simulation, you usually don't want to draw the full device. There are better ways to simulate, especially for the Bragg grating in this example. We're going to leverage the Lumerical EME solver, so we won't have to draw the full device length. Instead, we can just draw a unit cell, for example, something right here like this, and we can artificially propagate it as many times as we want to represent how many cells there are. And that's a way more efficient way to produce your simulation results than it is to draw the full thing. So to do that, we also have to make sure what we export to Lumerical is something reasonable. Otherwise, we're just using a lot of memory for no reason. So simulation geometry will be a Boolean property. We'll set the default to false, and then we'll add a comment here telling us that enable to draw geometry for simulation. And then what we'll also want to do is we'll also want to add in 2 more variables called x position and y position. And the reasoning for this is because later on when we draw our simulation, or if we're going to create circuits, we need to be able to place this device at different points in space. Without this, it might be harder to do so. This is an easier way you can do it. So this value will be a number property. because it can be any number. And the default will be a 0. We'll add 0.0 here to remind us that it can be a decimal. And then the comment will be device position X. And then in the same way, you can copy it down and say device position Y. And what we want to do now is we want to go to every one of these X, Y coordinate locations and add that in. So for the grating here, we'll add self.x position plus everything else, and the Y will be self.y position. And we'll do the same here for the waveguide, self.x position plus everything, self.y position. And we'll copy it here. And we'll also want to make sure that our ports also do the same thing, self.x position and self.y. And here will be self.x position plus that and self.y. And then a final check, we'll just run our script. And everything should be the same. So things look good in the visualizer. We'll look at it in the GDS. Yep, things look like they're correct. Yeah, and with that, we'll come to the end of this video. Thanks for watching.